Recording for this for us. So we're going to talk about several things. We're going to get into the idea of waves and oscillations, which we kind of started already in 13.1 and 2. We looked at the period. Focus up here, please. We looked at the period, or the length of time, right, it takes for an actual oscillation to occur. We talked about a mass spring system, and we talked about a pendulum system. And we talked about the fact that those two things are analogous to one another. When I pull on a spring, it's the same thing as taking a pendulum and raising it up to a certain height and letting them both go, and then they both oscillate back and forth. You saw yesterday in the lab when you took the data for the pendulum, what was the one thing that affected the time it takes for a pendulum to swing?
String length.
Yeah, string length. And that was the only thing that mattered, actually, which was kind of odd. I mean, if I were a student and I were doing this lab, I would have thought the angle would have mattered when you raised it to 50. And it turns out that by changing that angle, you're giving it more potential energy. So it ends up taking the same amount of time because it picks up speed for a longer period of time. It reaches a higher max speed, so you end up getting around the same period. And then the mass, right? The mass did not affect it at all. And that's kind of obvious because it's not in the formula. So we're going to continue that lesson today with this. So we're going to talk about pulse waves and periodic waves. We're going to differentiate between transverse and longitudinal. These are going to be some key words we're going to use. We've already talked about frequency, or we'll talk about now frequency with speed and wavelength, and then energy and amplitude, the size of the wave, the height of it. And then we'll talk about this concept called superposition, which leads us to constructive and destructive interference. Superposition is something that you'll continue to use outside of just physics, but continuing into engineering if you do study engineering. It's just one of our basic principles. Yeah?
When is this homework going to be due?
Check move. It's on there. I think your class is due a different date than the other class. I think I have you guys due on like Friday at like noon or 3 p.m. Because you guys don't have school on Friday, right? So I put a time on there.
Okay.
So take a look at that. 3? Yeah. Anyhow, all right, so let's quickly look at some definitions. So first, wave. When we talk about a wave, what we're talking about is simply a disturbance. A disturbance. But what we're doing is we're tracking the motion of that disturbance. Okay, so a wave is simply the tracking of the motion of a disturbance. And if you've ever, I'm trying to think of a good movie that has this in it. I feel like I've seen a movie when I was a kid, I don't know what movie it is, where a person rings a gong. You know what a gong is, where they take like a mallet and they hit this like metal plate, it goes boom, and you kind of see the disc kind of vibrate and oscillate. So what we're talking about is some sort of a physical motion. Or if you've ever taken a rock and throw it into a pond, and if the pond is perfectly still, it'll land in the center, and you'll see that ripple out effect. That's the concept of a wave. That wave is physically being tracked by its amplitude. So when we talk about wave here, we're specifically talking about that. What about when I talk about medium? We've used the phrase before in bio and chem. When I say the medium, what are we referring to scientifically now, not, the medium that you talk to other people and other spirits, right? It's another word, definition of medium. How about a medium in science? You remember from chem or bio what the medium is? Okay, you're on the right track. Give us what she said, the type of object or what it is. It's more of a material that the object or wave travels through. And what it's made of is a big important part here. So when we talk about different media, media is the actual substance that the wave is carried by. So for example, sound waves, I'm speaking right now, the medium that I'm speaking to you through is what? What's around us? What we say is around us physically. Just air, right? A gas of some sort. But can't you also talk underwater? I know it's hard to, but have you ever been underwater in the pool and tried to talk to someone? You hear something, but you don't hear exactly what they're saying. Well, boats actually use sound underwater, right? That's what boats do. If you've ever been on a boat before, they use sonar waves. They're sound waves. And sound waves that propagate through the water, and it can give you an idea of what the surface is like on the bottom of the water. So if you're fishing or some application of boating, anybody into fishing or boating here? Okay, so that doesn't work too well. I'm not personally, but I know the past some people have. So it's a good example because sound waves travel differently in different media. So the media is the stuff that you're traveling through, A mechanical wave, we have to consider the fact that the medium has to be deformable. So a mechanical wave is just a wave that requires a deformable medium. So for example, when I was just giving the example of sound, when I speak, what's happening is I'm vibrating the air molecules that are then vibrating further air molecules, and the sound is being propagated outward. And it's like a chain reaction until it reaches your eardrum, which interprets that vibration as some sort of a sound. And your brain has like a transform box in your brain. If you go on to study engineering, you talk about the function boxes. Your brain is like that. It takes some signal that makes no sense and turns it into something coherent for you. That's what's happening physically every time. So in this case, when we talk about mechanical waves, when you speak, you physically cause vibrations in the molecules in the air. So sound is an example of a mechanical wave because it requires a medium that can be deformed or changed. If you're in outer space, and you know anything about first of all, what is outer space made up of? What's the one word we use to represent outer space? It's in movies sometimes. Space is a blank. Space can be considered a what? When you take all the air out of something.
Void.
A void, good, that's a good word. Vacuum. Void, vacuum, both work. Very good. So a vacuum. If you try to yell or scream, obviously you wouldn't ever be in space without a spacesuit on if you were an astronaut, but hypothetically, if you were, or if you were an astronaut and you tried to ring a gong in space, no sound would actually occur at all. Because there's no physical mechanical wave traveling through there because the medium is not deformable. The sound wave will not propagate. So an example of mechanical, we said, is sound. An example of a wave that's not mechanical, so you understand the difference here, we're going to talk about this more in the next chapter, is light waves. And the reason we know that light, or EM spectrum in general, is not mechanical is because to get from the sun to the earth, the light has to travel through a vacuum. Okay, and a vacuum is not a deformable medium, meaning there's no substance there physically. So mechanical waves examples are sound waves or pulse waves. We'll talk about in a little bit. We'll get to pulses here. So a pulse, the idea is that when you send one single wave, and we're going to do a couple examples in a minute. I'll invite maybe one or two of you up to help with it. But a pulse is a single disturbance or a single wave. Single disturbance or single wave. Whereas periodic, the one below it, is some sort of a source that generates waves. Continuous generation of waves via some source. So for example, if you've ever seen the inner workings of a car engine, you'll see pistons moving up and down, right? When the engine is rotating, the engine's actually turning, which causes your axles to turn when you want them to. But what's happening is there are pistons that are firing over and over again. That's a controlled, forced frequency, meaning it's controlled. There are little mini explosions occurring every time. And that's causing these pistons to go up and down. And as a result, that would be an example of a periodic wave. That would cause what we're going to see, or what you're going to see actually pretty soon in your math class, as sinusoidal functions. And sinusoidal is a fancy word meaning sine or cosine. Okay? So a periodic wave, just to give you a little quick look, this is not drawn to scale, okay? This is one where the amplitudes are reasonable for each one, and I'm seeing that there's a bit of a change in period length as I go through here. So it doesn't have to be consistent at all. I could draw any wave, but as long as it's continuing to produce itself, it's a periodic wave. And that wave can be produced in different ways. It can be produced initially with a high frequency and then a lower frequency. So these variables can change, the widths and the heights of each of them.
Is it like when you're in the hospital?
Yeah, that's a great example of that. Yeah, perfect. What is the actual called? Anybody know in the hospital when they're measuring your pulse?
I just can't remember the name.
What's the actual machine called? Anyone? I don't even know the machine. And something? You can look it up, tell us. Yeah, but that's a great example of that. That's what's happening in the hospital. They're constantly measuring your pulse, right? So you see a readout of that, so it looks like a periodic wave. Because what's happening is your heart is constantly producing some sort of a wave. It's a pulse, okay? But it's a pulse that's occurring over and over and over and over, becoming periodic. All right, let's go on to the next slide, take a look. So this is where we have to start looking at the two different examples of waves. And I'll invite maybe one or two of you to help me with this first. So a transverse wave is the one we're going to start with. And a transverse wave involves vibrations that are perpendicular to the motion of the wave. Perpendicular to the motion. So for example, the example with a pebble thrown into a pond. When you throw the pebble, right, it lands in the center of the pond, and you see the ripples come out like this. So the water is technically oscillating up and down. That's physically what's happening. If you've been in a wave when you were a kid, did you ever make a wave pool? It's like a thing, I swear we did this when we were kids. You would like just make as much waves in the pool as possible, right? And the best way to do it would be to grab like a boogie board or surfboard or something like that and sit there and just keep like pushing the water up and down, and you create these currents. And when they meet together, you get this little amplified current. We'll see that in a minute with superposition. But that's what we're talking about here. The wave is propagating that way, yet the water is oscillating up and down. So it looks like the wave is traveling like this, but really the water is doing this while the wave is doing this. And if I look at those directions, I can see that they're perpendicular to each other. Because again, the vibrations of the particles are perpendicular, meaning up and down, and the wave moves left to right. Some examples besides that, I think of a good one. I'm going to use a slinky in a minute so you can actually do this. I'm trying to think of a good one. Oh, here's a good one for you. And it's actually involved with the slinky. There are some new workout techniques that people like to exercise where you use actually rope to strengthen your body. You've seen these before? Yeah. And you literally have to lift up, the rope is very heavy, and you'll see people training and literally whipping ropes, and what they're doing is they're generating force, which is exercising their arms, but it takes a lot of force to physically do that. But that's what they're actually generating, they're transverse waves. EM waves, which we're going to again talk about a chapter from now, electromagnetic waves, are just actually two transverse waves running perpendicular to each other. An electric wave and EM, magnetic wave. A magnetic wave. And the actual two pieces go together as two transverse waves. So how would I generate a transverse wave with a slinky? How would I generate a transverse wave? And this is kind of, to be honest, this is the easier one. The next one's a little harder. How would I generate this wave that we're looking at with a slinky based on the definition? The oscillations or vibrations should be perpendicular to the motion of the wave. What do you think we should do with this? I'm not going to just, put over steps, because that's just watching it happen. It's cool, but it's not what we're doing here, right? How would I do it? What do you think, Alex?
Goes one, goes up, and then it goes down.
Yeah, you pretty much have to raise one side up, and then hopefully it'll push the other side down. So why don't you, two volunteers, hold the other end of the slinky, okay? So, and it's very easy to use a slinky to demonstrate this, because the wave propagates very easily. So Alex, why don't you just go like this with your arm? Yeah, and take a look. So what he did, and it looks like the wave moved left to right, which it did, but the motion of his arm, again, the motion of his arm is up and down. Send a nice one. Let's let it settle out for a second. Send a nice small one, just a very small ripple. Yeah. Okay, we can kind of see it. Yeah, you can do a forcible. Keep going, yeah. So you can do and you can actually get standing waves to occur. If you keep going, if you keep going over and over again, you'll actually get standing waves and you'll get a little road to it here. But what's happening here, let's just settle out for a second. What's happening here is that Alex is vibrating his hand up and down. So it's causing a disturbance vertically. Yet the wave itself is traveling horizontally. That's where the perpendicular nature of this wave comes into play. Let's try to get this. So let's go nice and slow. And we want to try and get it so that we're in sync. And if we're in sync, what will happen is there'll be a point in the wave where it'll just start oscillating. You've seen this with music, right? It'll start oscillating up and down, and certain parts will be what we call nodes. They'll be standing. So let's try and get this going. Okay, look at the very center. If you look at the very center where Chris is kind of, you'll see that that part is not really moving. Chris, can you point out the part that's not moving right in the middle there? It's really not actually moving at all. But this part is going up and down. So the part closer to me on this half was oscillating up and then back down, and then up and then back down, kind of like a guitar string. If you played guitar before and you pluck on the string, it actually oscillates up and down, and the two ends are where you actually hold it. So if you want to change the pitch of the note, you move your hand along the guitar to make the guitar string shorter, and you get a higher pitched note. So that's physically what you're seeing here, and that's a transverse wave. Now this is the easier version of the wave, so I wanted to make sure that was clear. Before I go to the next wave, let's look at this diagram on the bottom right. Okay, some of the words we've talked about already, some are not, things that we've learned. So we've talked already about amplitude. Okay, we've used the phrase amplitude. That had to do with the displacement from equilibrium. So it's for the pendulum, it's the angle you raise it. Or for a mass spring system, it's how far you stretch the spring. That was the amplitude. Well, this amplitude is the same thing. Okay, so this is like the measurement of how far you are from the x-axis. The x-axis is like your equilibrium. If the wave is far away from equilibrium, it's like the spring that has been stretched all the way. You let go of the spring, it starts to oscillate. And it goes back and forth, back and forth. Every time it crosses equilibrium, That's where it's crossing your x-axis here. I'm calling it x-axis because it's labeled as x for now. Let's just say the horizontal axis, really, because this could be a function of time, which it usually is. So every time it crosses here, it's reaching back to where equilibrium was. These terms are rather old terms, but they're useful in physics, not as much in math. In math, you're going to call this the minimum value. Okay, we call it the trough in physics. In math, you call this a maximum value, or a crest. And because, notice, the maximum value occurs over and over and over again, you're going to hear a word later in math that calls these local maximums, meaning that in the neighborhood of that region, it is the greatest value. Everything around it is a little bit lower. And then this is a minimum in its neighborhood. But these are all the same minimum values, because this graph we're going to see, and you're going to see more in the fourth quarter, it literally goes on forever. That's the whole idea of a cyclical function, like a sine or cosine function. It will continue over and over and over. You'll see little nuances to that with tangent functions and other ones that have some issues along the way, and those have to do with zero in the denominator. But for now, what you want to be pointing out is the fact that you have crests and troughs as max and mins, and the distance between each successive crest is called a wavelength. Each successive trough is called a wavelength. This symbol, anybody know this symbol? Anybody know what that symbol is called?
I know it's half, half-life.
It might actually in chemistry use it. Is it for half-life? So another use of it. Yeah, anybody, the name of it is lambda. The symbol is lambda. So if you want to just, because I'm going to use that phrase a lot, if you're writing phonetics down, L-A-M-B-D-A, that's like kind of the way you pronounce it. Is that the way it's spelled, lambda? I wasn't sure. I'm trying to think about it. But phonetically, you're going to hear me say it a lot, okay? But this symbol is called lambda here. So I would draw this, if I'm drawing it just to be consistent, like that. Just like a wishbone, okay? Again, wavelength. And what is length measured in? Generally, what is length measured in? What do we use? What units? What did we use yesterday? What units? Yeah, so in general, though, general unit? Meters. So lambda is going to be a measurement, or wavelength is going to be a measurement in meters. How about amplitude? How about amplitude? We talked about the fact that amplitude, something about its units we went over the other day. What would the units of amplitude be if I'm measuring how far a pendulum is raised up? What unit would I measure to measure how far it's raised up? Degrees, very good. So it's some sort of an angular measurement. Or if it's a spring that I'm stretching, I stretch it by a certain amount of meters. And then I think I went over the example in sound, right? For sound waves carry more energy when they have a higher decibel level. So units of amplitude can vary based on what the wave itself is. Okay, units of amplitude can vary based on the actual wave itself. Okay. Let's take a look at the second type of wave now, and this one's a little bit trickier. It's called a longitudinal wave. And the idea here is that instead of the vibrations being perpendicular to the motion of the wave, they're now parallel to the motion of the wave. And parallel has the letter L in it, works out nicely with the word longitudinal. Transverse has the letter T in it, T is perpendicular, the last one was perpendicular. So make the mnemonic connection right now, right? You make a device so you know that. So longitudinal is going to be parallel. But what does that mean is the question. Like you can memorize this all day long, but what does it mean for the vibration to occur parallel to the motion? So let me give you an example. How many of you have been on a long line at some point in time? You wait at a store, right? Let's say 20 people or more. Has anybody been on line 20 people or more, maybe for a concert or for tickets or for a new iPhone or something, right? Okay, so you're online for a while, and let's say that the Apple store is allowing 10 people every time they allow a new set of people in. It's 10 at a time every time. They wait for the next 10 to leave, and then 10 more go in. So when they allow 10 people to go in, let's say I'm person number 11, and I'm sitting here distracted by my phone, or I'm talking to somebody, and the 10 people in front of me all walk in. There's a big gap now between me and the door. Everybody you know is going to say, come on, move up. You don't want to lose your spot in the line. So they're going to tell you to move up right away. So if there's a gap of 10 people and I start moving up, what am I doing? I'm creating space between me and the person behind me. Then they see me moving, right? And then they start moving after I do. And then the third person, or the 13th person, because the 10 went in already, moves after that person. And there's always a little delay, right? It's the same thing so you guys don't drive yet. Who actually is the permit? I've asked this question. Okay. So if you've been driving at a stoplight, it's the exact same thing, right? The way we would actually get rid of any sort of traffic would be to remove humans altogether. I think I put that video on Newsform, by the way. Take a look at Newsform. It's a cool video on getting rid of traffic. But the idea is that there's always a small delay in your response. So if you're in a car and the person in front of you starts to go, you don't go instantly. You kind of wait for them to move before you go, or else you might rear end them, right? But if the computer system ran it, it would automatically move perfectly every time. But if you think about this gap, and then the next person goes, then the next person goes, the next person goes, what you're seeing is you're seeing like a spread out of the line, and then the line condenses. And then the next person spreads out a little, the next person follows, condensing. So what you're seeing is this oscillatory motion, but it's moving in the same direction as the line is moving. So that's what this demonstration is trying to show. And I think it'll be best if we do another example of this, because this actually works well with this one. Anybody have any suggestion as to how I can do it though with this one? Because last time we extended the spring, right? It's like it went like that. What do you think I should do with this one?
Just push it horizontal.
Yeah, why don't you help me? Good. I agree. So let's get it set up nice and easily first. Hold on. Okay, so send me one pulse. Go ahead. Yeah, and that's exactly right. So all Peter is doing, let's put it down so it settles out. All Peter is doing is just sending a quick pulse. Okay, and that pulse is getting sent back and forth. Notice he's not doing this transverse, right? That's transverse. Let's put that one back down. What he's doing is he's disturbing the medium in the direction that the wave is going to move. So it's physically condensing and then expanding, condensing, expanding, condensing, expanding. So the vibration of the particles is occurring in this direction, and the wave is also moving in this direction. So what you're seeing here is the compressed part of the spring, the stretched part of the spring, and then the wave passes through here. It's now compressed, and then it goes beyond this, which leaves it stretched. So that's what we're talking about for longitudinal waves. When I referenced sound waves at the beginning of the period, I was talking about longitudinal waves. Because what I'm physically doing is I'm disturbing one molecule, which is disturbing the next, which is disturbing the next, but it's happening at the speed of sound. 343 meters per second. I mean, think about that. The back of the room is 5 meters from me, maybe 6. Sound moves at 343 meters in a second. So that's why the instant I speak, anyone in the room can hear. But if you've ever yelled to somebody and you hear like an echo and stuff, it's because the speed of sound can be delayed at times, and you might hear it a little bit later because your distance is so great. And if you've ever been, how many people have been out before when there's lightning, and you track the difference between the sight of lightning and the sound of lightning? What's the rule of thumb? Anyone know?
When you see the lightning counts, and if it's closest to, the more you count, the further away it is.
Exactly. Very good, Alex. The longer it takes for the delay between the actual seeing of the lightning, which travels at 3 times 10 to the 8 meters per second, compared to the sound, which is like 3 times 10 to the 2, right? A very small number compared to that. It takes a big significant difference. You know the actual number to use? Anyone know that number? You can derive it, and I've done it in the past, but we haven't got the M waves yet, so I won't derive it. But it's about a second for every mile. Okay, about a second differential. So if there's about a second between when you see lightning and when you hear lightning, it's about a mile away, because of the differential in the two speeds. That's all you're really looking at there. Okay, but the idea here is that sound waves themselves travel in that fashion. Another example, and you've all seen action movies before, whenever you see a big explosion, right? You see the main character get like blasted away from the explosion. In reality, it is true, they would get blasted away. And that's because of what are called pressure waves. So if there's some sort of an explosion, the air around the explosion exhibits high pressure. And those pressure fronts push outward. And eventually they do dissipate. They don't reach, they don't go on forever. And you'll see like what's called a blast radius of something. And the same thing is for underwater. If you have fault lines underwater, have you ever seen like where tsunamis form? They form because of earthquakes underwater and the fault lines are rushing against each other. Whenever you see where the one plate kind of grinds up on top of the other plate, a lot of pressure is released. And that's what causes tsunamis to actually occur. It changes if they're different. If they're just moving left to right, it's actually not as effective, or it's not as traumatic, or not as detrimental as when a fault plate actually slips over the other one. What is this referring to here? You see density here and X, and then look at this one. Can anybody make a connection here? Why are we using a wave to look at this? Like we saw the actual thing before, but what's going on with these two graphs here? Anybody pick up on what the correlation is? And just use your units or use your labels of your axes. This is graphing density. And think to yourself, density of what in this case? versus x, which is position. What do you think?
We're just looking at the spring when it's compressed. It's more dense, so it's positive. It's not wide and downstretched. It's down below the x.
Yeah, so what he's physically doing, like he said, Steve said, look, it's compressed. That's high density. When things are all gathered together, it's a high density. When they're separated and spread out like a gas is, it's very low density. That's this here. So what we're seeing is very high density, very low density, very high density, very low density. Now, the density line, this may not be a zero line. This may just be an axis here. But again, we're not looking at numbers. We're just talking about a wave that goes up and then down. And this is mapping the density of the spring as an example. All right. Let's see if there's any other examples I wanted to give you. No. So let's get into a little bit of math for now. Now that we got the theory. I mentioned it to the class. This is the lightest test in math for the year, just to give you a heads up. So for those that struggled a little bit with math in the past, this one is very light in the sense that there's not too much that we're going to go beyond what we're doing in class. Whereas in the last chapter, if you remember with circular motion, that got a little more confusing. You have to go back to forces from earlier in the semester. Not as much of it going on here. So this is just a quick derivation of what we're talking about with the speed of a wave. And if we start with our basic formula, right? Start with our basic formula. Velocity is equal to displacement over time. If I'm thinking about a wave, its displacement is measured in meters. Well, that's just the wavelength measured in meters. And if I think about the time it takes, time is just measured in seconds. Well, the period of a wave is measured in seconds. So I can replace those two variables right away. I can replace x with lambda and t with tau. So now I have velocity equals wavelength over period. But then, and so I can use this formula. Okay, again, I can use this formula. It's very useful. But then I can also recognize that there's another way to write this formula down. I can see here that I can replace period with 1 over the frequency. And that was from section 13.1, 13.2. We already used this formula at the top right. I'll write it. Okay, the period equals 1 over the frequency. So I'm replacing the period, which is given right here, with 1 over the frequency. And when I divide by something that's in a denominator, I have to remember that I'm really multiplying by a reciprocal. So when I think about this, right, this velocity is really lambda times omega over 1. Okay, because again, it was really v equals lambda divided by this, right? That's what it says up top. It says lambda divided by 1 over omega, but division means multiplied by the reciprocal. So this velocity becomes lambda times omega, the frequency, and that's the last formula we're going to have here. So if you look at your formula sheet, this is what you're going to see. Okay, you're going to see what's circled in black. Okay, that's what you're going to see on your formula sheet. But again, what's in blue could be used also. And you could always figure out if you have the frequency or if you have the actual period, you could find the frequency or vice versa. So this is the formula that we're going to utilize for the velocity of a wave. The product of the actual frequency and the wavelength. The frequency and the wavelength, those two things. How do I know the units are right? How do I know the units match up? We always do this with little formulas, right? We write our units out to make sure the dimensions are true. So if I look at the formula in black, what are the units for V? Units for V, what are they? Meters per second. So right away I know that's meters per second. Agreed? Units for omega.
Hertz.
Hertz, very good. It's a tough one to remember, and we'll talk about that again in a second. And then finally, we already wrote this down a minute ago, but units for wavelength, units for that would be meters. So at first it looks like, how does this work out, right? That doesn't match up. How is a hertz times a meter equal to meter per second, right?
Hertz is also like seconds to the negative first power.
Very good. Well done. Hertz is known as, we discussed, as cycles per second. Remember, hertz is a frequency. It's how many cycles occur. So what Rain said is his second to the negative 1. What we'll write for now is just 1 over seconds to show this. Okay, so again, hertz is cycles, which is just the number 1. There's no unit for cycles, per second. So we have 1 over seconds times meters, okay, which simply becomes 1 times meter over second. Meters per second equals meters per second. So the actual formula is dimensionally true, or dimensionally valid. Okay, we've done the dimensional analysis to prove that this is right. But again, good point there. Isabella, hertz for frequency, and then rain, 1/seconds is really hertz. To recognize that. And you should recognize that really, especially because yesterday in the double period lab, you had to work with hertz, right? You should have recognized the units were there, and we also did this in the last section. So a very, very simple math problem to start. So the reason I use this example, I played the trumpet in high school, so I just happened to look up the value. Bless you. I look up the value here just to get an idea for this. Okay, in a minute though, we'll do one that's a little more applicable. So first, we'll say the length of a sound wave produced by a middle C on a trumpet is approximately 0.72 meters. That's actually pretty long. I mean, a meter is about this big. So a sound wave from a trumpet, middle C, which is like a concert B flat, that actual value, that actual note itself is this long in wavelength. So when you think about wavelengths, you're going to start talking about pitches and frequencies, and we're going to see that here. So if the speed of the sound in the air is 343 meters per second, find its frequency or its pitch of this note. We have frequency or pitch. So what do we have for givens? What's the first given that we know? What do you got, Alex? Say again? Lambda?
Lambda is 0.772 meters.
Very good. And if you didn't even recognize that, right? If you didn't recognize right away that that was what it was, look at the actual unit. It's in meters. So as soon as Alex saw meters, he thought that's a length, and we're talking about wavelength, and wavelength is lambda. So again, use your units to help you know what you're working with. Other given? Velocity, right? Meters per second. So that's 343. We're looking for the frequency. What variable is frequency? Good. We have this little W looking thing, right? Omega, W. The frequency itself. Excuse me. What's the formula? And from the last slide, we'll go ahead and put it in. Very simple, right? V equals, Steve? Omega lambda. Okay, just simply solve this. We're trying to find omega. Let's divide both sides by lambda, and we'll get omega. Now, this is an easy example. It's not as applicable an example. In a minute, we'll do one with scientific notation and something that involves like some sort of medicine that we're going to talk about, x-rays. So for now, just calculate what this comes out to be. We got 343 divided by 0.72. .476 hertz. Very good. Hertz. Don't give him a Hertz donut. I heard that. I was about to ask about that, if you guys ever heard that before. That was the thing when I was in high school. Ask someone if they want a Hertz donut. If you nobody's ever asked that before, let them ask it to you, but ask it to you nicely. And you'll know what I mean if you say nicely. So 476 hertz, 476 hertz. Again, if I want to take a look at my dimensions, meters and meters cancel. Right? When I cancel something, I'm always left with a 1. So there's really a 1 up here, which leaves my units as 1/seconds. And as Rain mentioned a minute ago, 1/seconds is really hertz. Okay, so this is the frequency of this middle C on a trumpet, which is the frequency. Let's take a look at it now. That has you do the X-ray itself. And the reason I push this one is because I want to talk about prefixes for a little while. I want to talk about something that makes sense as to why the answer is the value it actually turns out to be also. So like an application of it. So in this case, we're going to take a look at wavelengths of X-rays. We're told that the frequency is 3 × 10⁻12 megahertz. Megahertz. I'm emphasizing the word mega. Anybody? This is one of the ones we have not used all year, but I said the first day of school, I was like, you're probably going to use this later in the year. We're starting to use mega. We're going to start to use giga. We're going to probably use nano and micro a lot now, ones that we didn't use. We used mainly kilo, right? And we used centi and milli so far, because we've been on mechanics. Good. It's a million or 10⁻⁶. Very good. A million or 10⁻⁶. And if you recall, I showed you a little technique that a lot of these ones that we're going to use go up by 3s, right? Go up by 10⁻�3. So if you forget kilo, 10⁻�3, mega, 10⁻⁶, giga, 10⁻⁹, and then tera, which we're not going to use much of, is 10⁻⁻12. You would use tera if you were talking about like computer storage, okay, or very, very, very large numbers. As soon as you get to long enough lengths that aren't worth measuring in kilometers, you go into light years. So this is not as widely used as a unit. And then on the other end, we can also talk about ones that we've used already. Right? We've talked about milli already and centi. Centi's 10 to the negative 2. Milli's 10 to the negative 3. We have not talked about this one yet. We have not talked about the next one yet, but anybody remember what was after milli? And I'll tell you right now, it was not negative 4, it was negative 6. Anybody remember what that was called?
Pico.
Not pico. Pico's way further. That's 10 to the negative 12. But that's good. It is smaller. You're right. It's definitely smaller. It's micro. Very good. Micro. And the symbol is like the mu symbol. Remember from friction? It's the same symbol. So when you see micro, we're going to use micro soon actually. For electric fields, we're going to talk about microcoulomb charges. Micro is 10 to the negative 6. And there's one more. There's one more. It's 10 to the negative 9 that's very widely used today. Nano. Okay, and beyond that is actually used right now. Okay? But the concept of a micrometer or micrometer comes from the fact that what do you use to see things at that level? In bio and chem, what do you physically use? A microscope. That's the reason for the name of it, right? You're seeing things on the order of 10 to the negative 6 meters. So when you talk about nanotechnology, it's just a fancy way of saying technology that is being developed on a scale that is so small that they can change things about the molecules themselves. So when you talk about nanocarbon tubes and stuff, these new materials that are super strong but very lightweight, it has to do with things that are being developed on a very small level. Now, for mega, we see mega is 10 to the 6. So we're going to replace that capital M with 10 to the 6. And the easiest way to do it is to literally just rewrite this as 3 times 10 to the 12 times 10 to the 6 hertz. And then obviously, if I have the same base and I'm multiplying two things, I can just add the exponents. Okay, add the exponents. So this becomes really a frequency of 3 times 10 to the 18 hertz. So that's our frequency that we're going to use in this problem. So for now, I don't really need these two, just to remind myself that I've already converted. So I've got my frequency that I need. It's got to be in base units. It's in base units now. I can then go on and say, all right, what else do I have? I'm told that all EM waves travel at the speed of light. And there's the speed of light, 3 times 10 to the 8. So I see speed of light. Speed makes me think of velocity. This is the velocity of the wave. And we're trying to find the actual wavelength. Okay, our goal is to figure out what is lambda in this case. What is lambda? So try this on your calculator. I want to make sure we're all clear on scientific notation. Last test, there were like 10 mistakes out of 28 students on simply calculations. Just on calculations for scientific notation. And it wasn't the math you did on the test, it was the calculator. You got to practice the calculator working with this. If you don't know how to use the EE tool on the calculator, let me know. You should not be typing 10 to the 18. You should not be typing in times 10 to the 8. Use the EE tool. If you have no idea what I'm saying right now, just raise your hand. I'll come by and show you that EE tool. Much faster, and you don't actually have any problem. See? Okay. So this, yeah, but there's a quick way to do it. So type 3 first. Now press second and hit the comma above the number set. And it'll bring up a capital letter E. You see that? And then just type in the number 8. And what that does is that replaces everything that you just did with times 10 to it. That literally responds as 3 times 10 to the 8. And if you hit enter, you'll see it's the exact same number as the way you did it if you did it the other way. So to prove to yourself if you want to. Same number, right? Yeah, so it's a really good feature to know on your calculator when you get very large or very small numbers. Right? We talked earlier in the year about scientific notation and went through all of that work, but we didn't always go through the practice in the calculator, and I noticed on the last test that some people were really struggling with that still. It was kind of an assumption I made that you understood, which was probably a misinformed assumption, right? I thought everybody knew that, but I'm just going to make sure that we all get it now. So if I want to calculate this in my calculator, I'll take a look and solve the formula. I've got V equals omega lambda. I'm trying to find lambda, so I've got V over omega here. Looks about right. So I've got 3 times 10 to the 8, which is V, over 3 times 10 to the 18. And this is measured in meters per second, and this is measured in 1/seconds, or hertz. So go ahead in your calculator and do this. Take this number, 3E8, hit the divide sign, and then do 3E18. 3E8 over 3E18. I recommend putting parentheses. Actually, let me think for a second. Does the E ignore the parentheses? I know if you didn't have this, you would need it. No, we're good. So the E automatically performs this operation first. You don't need parentheses around that denominator. I guess it's an automatic command, yeah. So do 3E8, divide by 3E18. You're going to get a very small number, right? And if we did this in our head, we can kind of see what's happening here too, right? Look, these cancel, that becomes a 1 and a 1. 10 to the 8 over 10 to the 18, you subtract your exponents. This becomes 10 to the negative 10, and this is still a 1 in front, and my units are meters. Okay, so you should have gotten something to this order, 1 times 10 to the negative 10. Depends on your mode, but you might have more or less decimals depending on what your mode is set up. Can anybody represent this in nanometers? Can we represent this in nanometers? What do you think it is in nanometers?
1 times 10 to the negative 1 nano.
Well done. Well done. Very good, Alex. And if you didn't see what Alex did, he probably did most of it in his head. You can use conversions like we did earlier in the year, or watch what I can just show you. Rewrite 10 to the negative 10 as 10 to the negative 1 times 10 to the negative 9. So it's literally the same thing. I'm not changing the value. If you do the math, this works out, right? I can add these two together, it still comes out to this. And as Alex just said a minute ago, 10 to the negative 9 means nano. So just replace this with the nano symbol, and that's what you're left with. Okay, exactly what Alex had said. 1 times 10 to the negative 1. So this is part of the reason I wanted to talk about this problem. Look at the length of a wavelength of an X-ray. Why do you think we use X-rays to measure if we have a broken bone or an issue in our body? Use this idea to help you. Okay, let's not use the word fast. Let's not use the word fast. I'm not talking about speed here, right? What is this referring to? What are the units representing? The physical length of the wave itself, right? Why do we use X-rays to measure things inside the body at the microscopic level? Why do we use X-rays?
Right, because the wavelength is so small, the frequency is much greater, so that can detect more.
Okay, so yeah, they are inversely related. So the frequency is very high for X-rays, when the wavelength is very, very small. Yeah, the size of the wave physically allows it to pass through the body. So when you get an X-ray taken, isn't there always some sort of a film behind you that they're actually taking a picture with? And if you don't want X-rays on your chest because you have a broken arm, what do you wear? How many's got an X-ray? What do you wear? Yeah, a lead vest. The lead does not allow those X-rays to go through your body, but through your arm. What shows up on the screen are the waves that actually made it through where you have cracks in your bone. Your bone has a different density than the rest of your body. So based on its density, it's going to detect differently on the back, right? Hey, listen, tomorrow, do I have you guys tomorrow? Yes. All right? Bring back. Yes? Okay. Tomorrow I want to finish up some of this, but what I'd like you to do tonight, again, is to take a look at that. So we're going to talk quickly about some theory behind this. So that's really all the math for this section, by the way. So this is not a heavy math test. You're noticing that already. 13.1 and 13.2, we had a couple formulas with period. Right? 2 pi root L over G, 2 pi root M over K, and then period equals 1 over frequency. Aside from what we just did a minute ago, that's the only math you really need to think about for this test. So this is a heavier theoretical test than it is mathematical. Now, with that said, you still need to recognize that Hooke's law Hooke's law is something that is useful for this test also. Okay, although we learned it earlier in the year with forces, you did it in your lab where you found the K value. Remember in the lab yesterday where you were trying to find the K value based on the stretch? So Hooke's law is also something that will probably show up in a math part, okay? Where you find something like a K value and then maybe use that K value for something else. So just keep that in the back of your mind. But now theory-wise, let's take a quick look at waves and energy. The idea here that I want you to see is that the wave itself carries energy. And the way to see that or think about it is if you've ever been in the ocean before, right? If you've been in the ocean and like an actual wave can pass you, but just like a little wake that's coming past you, the water rises up and then it falls back down, and that literally travels throughout the water. And when it gets to you, if you're on like a boogie board or some flotating device, you naturally get lifted up. And that's because the energy that the wave is physically carrying you is creating buoyant force underneath you, which lifts you up. So to visualize this concept, think about it that way. But the idea I want you to see, or mathematically understand, is that the energy that a wave actually creates is proportional to its amplitude squared. So a bigger amplitude simply means that the actual wave carries more energy. It happens to be the square of the amplitude, but the idea is that they are proportional to each other still. So you have a bigger amplitude, a bigger or larger amount of energy that's actually being carried. We also talk about the energy rate, the rate at which it does, and this is just a symbol I'll show you because I went over it in the other class. It's not something that you'll be tested on this last part, but this symbol, E dot, in engineering and calculus, you're going to see this a lot, that the dot stands for a rate with respect to time. So the energy that is actually being transferred with respect to time. And if you think about what that was, energy over time, that was just power. Okay, that was just power. So this also has to do with the amount of power that's actually generated. Physically, to see this also, you could think of a mass spring system or a pendulum. All right, think about a pendulum. When you take a pendulum to start, you raise it up to a certain amplitude and let go. The pendulum eventually stops because what's happening as it goes through the equilibrium position every time until it eventually stops at the bottom. What's physically happening? What is it doing? What is it doing? In terms of energy, what's happening each right? It's physically losing energy. Losing it to some sort of effect, whether it's air resistance, whether it's the friction in the actual cord at the top, but it's losing energy along the way. And we can think of amplitude as energy. Amplitude as energy. So as the pendulum swings back and forth over and over, it eventually stops here where it has no amplitude. When it's literally just hanging straight down, there is no amplitude in this case. So there would be no energy left because it's sitting still. Another example would be the mass spring system. When you pull on that spring, you let go, it eventually stops. Guys, stop. Whatever you're doing, stop, please. It eventually will stop, and it'll stop oscillating back and forth, and it will eventually come to rest. The idea, though, is to recognize that energy and amplitude are the things that are proportional to one another. If I were to physically pull on the spring further, I'm storing more energy in the spring, so when I let go, this actual spring will travel faster because it has more energy, because you gave it more amplitude in the beginning. Okay, so amplitude has to do with the amount of energy that's actually carried in the wave. This next idea is really applicable when you study electrical computer engineering. It's very useful if you're someone who might work in some sort of a broadcasting system, whether that be the actual engineer that works with the system or a person that actually works on it every day. So if you think about broadcasting radio waves and EM waves, they can get interfered sometimes. How many of you guys and one ladies play Xbox or PlayStation, one of the two systems? Only a couple, okay? I don't know if there are a lot of people that play games. Well, if you know, I don't know if you know this one, but when Xbox first started going to wireless controllers, it was with Xbox 360. And it was probably like, I don't know, 4 or 5 years ago when they went to wireless controllers. And one of the biggest problems originally was that the controllers themselves were actually getting interfered by phone lines. So if you know, like, do you guys still have house phones? Your parents have house lines? Some have landlines, some people don't have their landline anymore, right? Well, if you have an old landline, Old landlines are connected to the wall like this is, where there's a wire that comes out of the wall and you plug it into the back of the phone and you're set up. Now, the newer phones that use as landlines have like a hub, and then you could put like 5 other phones around the house, and those phones work off of the hub. They send some sort of a signal. It's like a satellite system, if you will, where the other phones operate based on the frequency of the hub itself. When Xbox started using its wireless controllers, they actually ran on the same frequency as the old satellite phones that used to work in houses. So there would be a lot of interference between them. So you'd be playing, and if you're on the phone at the same time as you're playing, and this happened in my house all the time, my 3 brothers would be playing on Xbox, somebody was always on the Xbox. And my mom would get upset because she'd try to use the phone, and there would actually be static on the line. And it would happen when you were using the wireless controllers, so whenever she was on the phone, we'd plug in the controllers and not use the wireless part. And believe it or not, it actually proved like a big significant difference. She would literally stop hearing static all of a sudden. And then eventually phones actually came out with their own frequency, and now it's called like DECT 6. It's like just a new frequency that's not using the same standard ones that remote controllers use. How many of you in your home have 2 different Wi-Fi signals at your house? What's the differentiating characteristic of the signal? What do you see at the very end of the signal usually? Do you notice anything different? Like at the name, it says, what does it say at the end? Yeah, it says like a 5G or something at the end, right?
And the other one is 3G.
And the other one says 2G, yeah. And that has to do with the frequency it's operating on. That's gigahertz. So it's operating on different frequencies. And what happens actually is the wavelengths themselves are different lengths because of the different frequencies they're operating on. And what you'll notice is that, I forget which way it works, to be honest, whether it's the 5 or the 2. One of them works really well in a close proximity of your router with a very high speed. The one without the 5G. So the 2G is actually a stronger signal. Most people think the higher number is stronger signal. And I think this doesn't make sense because I remember saying this. You get a better signal from the 2G line if you're close to the router. But what happens is that signal drops pretty quickly. So if you get within or outside of a certain radius of the actual router, your 2G signal will not be picking up at all. But the 5G you will still get beyond that. So if you go to your backyard, if you have a backyard, you'll see that the 5G signal will extend further, but it will not be as strong. It has to do with the different frequencies that the actual wavelength is actually operating on. Anyhow, so what am I getting at? I'm getting at interference because interference has to do with some sort of a EM, usually EM wave, electromagnetic wave, that gets interfered with, gets disturbed by some other sort of a signal, gets interacted with, you see. So the concept here that we want to talk about is called superposition. And superposition, it's really actually pretty interesting, and you've seen this before, actually. If you've ever been, I talked about the wave pool yesterday, right, in class with the boogie board. So if you've been in a wave pool, remember, like even in the ocean in general, when 2 waves come together, what happens? When like these 2 waves are traveling toward each other, or 2 wakes, let's just say, the wake of like 2 boats, when they're traveling toward each other, when they meet, what happens in the middle when they meet? You ever seen it in the ocean? Like literally 2 waves coming together, what happens eventually?
They crash and makes it bigger.
Yeah, they crash, they kind of like go up to a bigger wave, and then they kind of like just continue to pass through each other. So the concept here is called superposition. That's exactly that. It's when you have 2 waves that interfere with one another in either a constructive or destructive way. In a constructive or a destructive way. So the example in the water, with 2 wakes coming toward each other, they both have positive amplitudes, and therefore the resultant is a more positive amplitude wave. They sum together. So if the amplitude of this wave is a meter and this wave is a meter, when they cross paths, it'll be 2 meters suddenly, and then they'll continue to pass through each other, actually. Now, the opposite occurs if you have a positive amplitude with a negative amplitude. If this is positive 2, and this is negative 2, when they actually hit each other, what's going to happen? Yeah, there's nothing there, actually. The waves will disappear for a second, but then they'll continue to pass through each other. Okay? So the concept here is that we're going to look at 2 types of interference using what we're calling superposition principle, which is simply saying you can add the amplitudes together. Okay? So let's take a look at those 2 examples here. So the one on the left that we started with has 2 positive amplitudes coming together. Those 2 positive amplitudes, call them 3 and 2. A height of 3 and a height of 2. When combined, give you a height of simply 5. Okay? A height of simply 5. So in this example, what we're seeing, and I'll zoom in so we can see this a little bit better. What we're seeing with this example here is that this wave has a certain height, and so does this one, and they start to form together, so it goes A, B, C, D in that order. As they get closer to one another, they start to kind of combine, right? You can see the outline of the original wave there, the outline of this original wave here. But when they actually coincide, the sum of these two equals the resultant. So this is a height of 2, this is a height of, say, 3. Together they add up to a height of 5, or 2 and 4 gives you 6. Whatever numbers you want to use are fine right now. But what I want you to pick up on is that after they sum together, this wave that was originally traveling right with an amplitude of 3 still travels right with an amplitude of 3. And this one with left with an amplitude of 2 still goes left with an amplitude of 2. They kind of pass through each other. But for the moment when they coincide, they actually sum together to a bigger wave. So with the second example, destructive interference is literally the opposite. Call this a height of, say, 5. Call this a height of -2. 5 and -2 together would yield 3, and that's what this height is right here. Again, this is a height of 5, this is a height of -2. I'm simply adding 5 and -2 together, and it gives me a total of 3. So we can see that the resultant height actually got smaller because I had a big wave, positively big wave, and a negative wave. A positive and a negative partially cancel each other out, so the result is a little bit less than the first wave started with because of this negative wave that canceled it. And then after they actually line up, they continue to pass through each other, and this amplitude was -2, it's still -2. This amplitude was +3 to start, this is still +3. Whatever it was, it still is at the end, but for the moment when they coincide, the waves actually cancel one another out. Okay, they cancel each other out. Okay. Let's see. We have 2 other things to take a look at. This is something that you actually kind of did a little bit of discovery already of in your lab. So in that lab that you worked on, is that last night, you guys? Yeah. You worked on last night. You saw that you could change the end of the fixture. These are called fixed ends or free ends. We call them boundary conditions in math. If you take calculus next year, you'll talk about what are called the initial conditions and boundary conditions that are mathematically the same thing as this. It has to do with what the end is like of something. So this, if you think about it, and this is an opportunity for extra credit, by the way. I gave the other class an opportunity for it because they asked about it, so I'll tell you guys the same thing. I'll remind you at the end of this. But this example is showing, imagine something that's on the end where the end is actually considered a free boundary. If this wave is sent with a positive amplitude, it causes this rope to kick upward. And it kicks upward, but then it responds by pulling back down. So it moves up first, but then the tension in the rope and the weight of the knot will pull it back down, and it's as if you're sending a pulse back. So the incident pulse has a positive amplitude, and the reflected pulse also has a positive amplitude. But yet, with this example, this is the one you guys did in your lab, you notice that the incident pulse had a positive amplitude, but the reflected pulse had a negative amplitude. So if you want to demonstrate this and do a little extra credit, that's fine. So, and I've talked to you about extra credit already, it's just like a point or 2 on your test. So if you can make this apparatus, 2 of them, one like this and one like this, and it doesn't need to be physically like into the wall, but it has to not be able to move up and down. So maybe like you could start with a rope and tie a rope around like a pole of some sort, but you need to be able to give it enough force that when you flick it, it reaches the pole and it comes back. Okay, and you have to have somebody taking a video from the side so you can see the positive amplitude traveling. It'll kick this end up, and then it'll slide back down, and it'll send the same exact wave back. So I want to see this throughout the process. You probably want to use a rather short rope, actually, because if it's too long, the wave will lose its energy as it gets carried to the actual end. That's the first one. And then what you can do if you want is just take like a bunch of duct tape and tape this all together so that it's not able to slide up and down. And that's when you have this one. Okay, so you can demonstrate this if you want as an extra credit opportunity on the next test. If you're going to do that, though, do it before the next test, as always. So that's until next Wednesday you have time to do it. Submit it as a video file, explaining everything. Remember, if you just send a video and there's nothing to explanation, I might give you a point if it's even right. If it's done well and it's explained pretty well, I'll give you 2 points. If it's really done well, I'll give you 3 points before. That's a pretty decent chunk on the test. Okay, if your test is out of 40 points, 3 points out of 40 is actually a good amount. It's like an 8% curve on your test if you do a good job. So consider this as an extra credit if you want over the weekend. Okay, if you want to work with one other person, that's fine. The two of you can work together and just send me a video of the two of you. Maybe one person does one of them, and then the next person does the other, and then you explain it together in the video. It is very much like a lab. Yeah, this is pretty much like a lab. But I want you to physically do it for extra credit, not send me an animation of the lab. You know what I mean? So physically, I want to see it happen. I just gave an extra credit opportunity. Okay, so talk to your classmates before the end of the period or before you leave today so you get an idea of what it was. If it's not clear, ask me. Hey, last example for today. Okay, then we're actually done. We're done a little bit early today. This is an example that is just showing mixed interference. And it's showing an example of where you can have destructive or constructive interference. So let's start by looking at our legend in the top right. I'm going to zoom in for a minute. Let's look at our legend in the top right. The legend tells us that the green wave is wave 1, the blue wave is wave 2, and then red is a resultant. And we've used the word resultant before. It usually has to do with summing together two things. So take a look at this and give some labels first. Let's put some labels on these axes. So let's call this a height of 1. Let's call this a height of 2. Let's call this -1 and -2. I don't care about the horizontal axis. These don't need to be labeled, so don't worry about those. So let's give the heights some labels to start. Now, at any location you want, and you can pick a different location than I pick, but at any location, put a vertical line. So pick a spot somewhere along the way. Doesn't matter where, but put a vertical line somewhere. Okay, I'll put one arbitrarily, randomly somewhere, but you guys pick your own choice. So I'm going to pick, and it will work no matter where you put it. I'm going to pick right here. I'm going to put a vertical line there. And what I'm noticing right away is that the resultant wave is bigger than the actual original waves. Well, look at the original waves. This has a positive amplitude of maybe, let's see, go over here, that's like a third, or 0.3, or around 0.3. This amplitude, that's around 2/3. A third and 2/3 should give me a full. And if you take a look at the red line, it's around a height of 1. So what we're noticing here is that the amplitude of the blue plus the amplitude of the green equals the amplitude of the red line. Okay, and it's not always blue and green, I'm just giving this example here. But the two waves that are interfering with each other, can be summed together to give you what we're calling the resultant wave. Again, amplitude is the height of the wave. Some of you on that lab really confuse that still. Amplitude is the height of the wave. This, remember, is called the wavelength. That's the width of the wave. The height is the amplitude. So if I sum together the height of blue plus the height of green, I'll get the height of red. Now that's an example of constructive interference, because I'm taking two amplitudes that are both positive and making it more positive as a sum. Where would there be destructive interference? Chris, give me a general statement. Go ahead.
I think right where horizontally the third little mark, that would.
That looks good to me. I agree.
0.5 and -0.5.
Yeah, that looks reasonable. So it looks like here, the amplitude of the green wave is around 0.5. The amplitude of the blue wave is around -0.5. And as a result, 0.5 and -0.5 should give us 0. And the height of the red wave is exactly 0. Great.
The dash mark 6, if those differences exactly
Right here?
they just cancel each other out.
So what's happening here is that the blue wave and the green wave have amplitudes of 0. And what's 0 plus 0? So that's why the red wave also crosses there. Yep, absolutely. Okay? So this is a good example of destructive interference right here. And this was an example of constructive interference. Okay, there's many other examples anywhere along the way, right? Like here, that's destructive. That's destructive. When they're both on the negative side, though, it's constructive, just constructive negatively. So for example, here, that's constructive, that's destructive, that's destructive. This is the one that's most confusing to students because you think it's destructive. Destructive interference just means that one is positive and one is negative. amplitude-wise. If both amplitudes are negative, meaning this green and this blue line, this is an example of constructive interference still, but it's just that the sum is going to be negative. Right? This is like negative 0.1 plus negative 0.2 is equal to negative 0.3. It's still constructive interference, even though the red line is negative. It has to do with if these are on opposing sides, that we have destructive interference. Okay? Questions in general on this lesson? I'm thinking if there's anything else I wanted to add. I think that's it for me. Any questions on this topic? 13.3 and 4.
Wait, why is not the other one? Yeah, why is it
Destructive?
Yes.
Because the blue wave has a positive, the green wave has a negative. Whenever the waves you're adding together have opposite signs, it's destructive. So even here, green was positive, blue was negative, but either way, they were opposite signs, right? Here, opposite signs. But here, both green and blue are negative, and they add up to a more negative number. Becoming more negative is constructive. Becoming more positive is also constructive.